file. So hopefully we'll be able to see now. Yeah, now it is coming.
Yes, sir.
Okay. So now this class, which is the computation of high voltage fields by finite element method. Now the important thing is that this term finite element was first coined by a person called Cloud in 1960. So you can see that science does not depend on whatever computer is there or not. Science goes in its own way. So people were working on it. Uh, but the developments actually took place in the 1960s, and in this decade, people immediately found that FEM is very useful not only for one particular area but in multiple areas. For example, here it is written stress analysis, which can be used very effectively in civil engineering as well as mechanical engineering, then fluid flow, then heat transfer. So you can see the different very important areas. And then in the 70s, this method has been extended to much wider variety of problems. In fact, today, if you ask me, then uh, anything that we want to solve, finite element packages are able to do it. Almost anything. Development of these packages basically started late 70s and then in 1980s. And today, finite element method is one of the most important methods that is existing. Now, going into the basics of finite element method, as we have done in FDN, we have subdivided our region of interest into either it is a square or it is a rectangle. In three-dimensional cases, it's either a cube or it's a rectangular parallelepiped. So in this case, it's not those. That's not the way we subdivide. What we do is the entire region is subdivided into smaller sub-regions. There is a small difference here. That finite difference method, we are basically subdividing it into some nodes. Basically, we are generating the nodes and we are assuming some relationship of a variable between two connecting nodes. Whereas in finite element method, this concept is changed. We are not dependent here on nodes. Nodes are there, but we are subdividing it into small sub-regions, and within that region, we assume a relationship of the primary field variable. For example, in our case, it is electric potential. And of course, the governing equation has to be satisfied. That means it could be Laplace's equation, it could be Poisson's equation, or any other governing equation. Now, typically, let me show you what we do is explained in this diagram. This is a diagram I am showing for two-dimensional field. It is easier to understand. Now, on the left, we have the region of interest, which is the total area, let's say A. So what we are going to do is that we are subdividing into smaller sub-regions, but then immediately the question will come that smaller sub-region, what will be the shape of it? Yes, that's an important question, and there are different types of shapes people have used. But the most commonly used shape that FEM uses is a triangle. And if it is a three-dimensional case, then you cannot have a triangle. Then what we have is a tetrahedron. But the moment we say triangle, then we generate on the right hand side, you can see that this is the element domain. Then we say that the area of the element domain is dA, which is a small area, which is of course part of the region of interest. But then what we are going to define here is that this small subregion, in our case it's a triangle, it is called finite element. In FDM, you remember, it was the distance between the two nodes. That's why the name came finite difference. That is difference between the two nodes. Whereas here all the computation is over the element domain, not just the nodes. So we call it finite element. And the moment we say an element, naturally there has to be a boundary. So here it is shown that it's the element boundary, which is actually the boundary of the triangle. And since it is a triangle, then the three vertices of the triangle, they are the three nodes. And we define the value of the primary field variable, which in our case is electric potential, that is phi 1, phi 2, and phi 3 at these three vertices. And then we are going to define a relationship of the primary field variable over this element domain. Once again, a lot of different types of relationship can be defined, but most commonly used relationship is that the primary field variable has a linear relationship in the element domain. That means as you move from point to point, the value of the primary field variable will vary linearly. So once again, just like FDM, where between the two nodes we were assuming a linear distribution, here we are assuming a linear distribution, but not along the boundary, but along the element domain. Now, uh, how do we solve it? Because after all, then we have to solve the values not at all the points, but only at the vertices. And then after the solution, from the knowledge of the potential distribution, we can find out the values at any other point. So now the question is, how do we solve it? So several approaches are there. The if the physical here, if you see the highlighted line, if the physical formulation of the problem is in terms of a differential equation, which is typically Laplace's or the Poisson's equation, then the most popular method of formulation, that is the FEM formulation, is called the Galerkin method. But then there are other approaches also in FEM which are very powerful and very flexible. That is, if the physical problem can be formulated by minimization of a functional, I'll just explain it, then variational formulation of finite element is used. That means instead of going for a Galerkin formulation, we go for the variational formulation. Now the issue is we are saying minimization of a functional. Now what could be this functional which we can minimize? Now for problems that is involving high voltage fields, this functional is the energy stored. We all know that a condition for stability is the minimum energy condition. For example, if you throw a ball, you see that the ball drops couple of times, finally comes to a stop. Now, if you calculate the energy at different points, then you will find that the point where the ball stops, its energy is minimum. So same approach we follow here, that whatever be the potentials of the electrode, etc., the field is developed in such a way that energy stored in the electric field will always be minimum. That is the condition of stability. And therefore, when we say that our functional is energy stored, then we try to minimize this functional and solve it for the FEM formulation, and then we call it a variational approach for FEM. So, what we will explain today is what is called the variational approach. Right. But before that, once again, let me tell you that what are the procedural steps in FEM. That is always very important if we know what are the procedural steps. So here I have written 1, 2, 3, 4. So you can see number 1. As in the case of FDM, in the case of FEM, we first discretize the region of interest into finite elements. That is, we generate the meshes. Once again, these triangular mesh generators are so popular nowadays that we have very powerful mesh generators nowadays. So we use those mesh generators and we discretize the region of interest. Then suitable functions are considered to interpolate the field variable over the element. That means that element domain, we assume a relationship of the field variable. The most commonly used variable relationship is that the primary field variable, that is in our case electric potential, varies linearly over the element domain. Then we have take our formulation, whether it is Galerkin, whether it is variational, so we form the coefficient matrix, that is the matrix equation, of course satisfying the field condition. That means either it is satisfying the Laplace's of partials equation in Galerkin method, or by minimizing the energy of the field in the variational approach. And then we write the global system of equation for all the elements. And for this, there are certain things we have to follow, that what is the element connectivity. That means which node of element 1 is connected to which node of other element. That has to be known, but that is done by the mesh generators. Nothing is to be done by manually nowadays. So by mesh generation, we can have this connectivity and the global equation set is formed. Then we solve this global equation set and we get the values of the primary field variable, but not everywhere, but only at the vertices of the triangle, that is the FEM nodes. And if any other quantity has to be computed, then after the solution of the global equation system, we can use any known field equation or any mathematical technique like interpolation, and we can find out the other quantities. So with this background, I go to the variational approach towards effluent formulation. So once again, I repeat that in this approach, we follow that principle of minimum potential energy that will be used in this method. And what is this principle? It says that out of all possible potential functions, the one which minimizes the total potential energy is the potential solution that will satisfy equilibrium. So we go for this approach. Now, how do we do it? Well, let us go into the detailed computation, but before that, uh, I hope you all know that what is the energy stored in the electric field. If I ask this question, very often I get the answer that is half CV square. Well, it is not wrong, but it is, what should I say, that it cannot be used in every example. If it is a very simple capacitor, like a cylindrical capacitor or a parallel plate capacitor, it can be used. But it cannot be used for a complicated system. For that, we have a different equation. I hope you remember from your basic field theory that there is something called the energy density of electric field. That means energy stored per unit volume. That is half epsilon E square, where E is electric field intensity. Now, why is it so flexible, this equation? Because E, that is electric field intensity, it can be defined at one particular point. Whereas half CV square, for that we have to know first the potential difference, but that involves at least 2 points, and we have to know C for a given configuration. Whereas half epsilon is square, we just have to know the material property, which must be known, and E can be defined at a single point because E is always defined at one point. So we can assume a small volume around a point. That means in our case it is the element domain of small area dA. So half epsilon E square multiplied by the volume of the element domain will automatically become the total energy. That means, I repeat, go to this diagram here. So let's take this element domain on the right hand side. And since it is a small element domain, what we are saying that, let's say at the middle of this domain, our field intensity is E. So we are saying half epsilon E square. Then I need the volume of this element. How do I do it? Since it is a two-dimensional case, I again repeat what I told you earlier, that two-dimensional means the field is independent of the z-axis. So what we assume is that along the z-axis, I take a unit length 1. And what is the area of this element? dA. So dA into 1 will become the volume of this uh, element. So half epsilon is square multiplied by this volume, that becomes the energy of this element. But that's not the energy of this entire region of interest. Should I multiply this volume by n number of elements? The answer is no. Why? Because this region is not a small region. Because when we are solving a practical problem, this could be a large region. And therefore, the value of electric field intensity at the different elements are different. So we cannot multiply energy of one particular element multiplied by the number of elements. So what we have to do? You have to integrate. That means we integrate the energy of this element domain over the entire area A. So now I again come back to the equation. So you can see 15.1 half epsilon is square multiplied by the volume, where L is the perpendicular length perpendicular to the plane of the display. dA is the elemental area, and then we integrate it over the whole area. But as I said, that our target or our primary field variable is not E. Our primary field variable is electric potential, so we replace E by minus grad phi. So we convert it to electric potential. Now, in computerized terminology, this integration, we don't do it in the conventional way, because you all know that integration is nothing but summation. So for computerized technology, what we are going to do, we take all the elements, we take the energies and simply sum it up. It will be like energy 1 plus energy 2 into like energy n. We add all of them, we get the total energy. That's the integration in our computerized technology. So the total energy we calculate 15.3 by simply summing up the elemental energy from 1 to n. Now, to minimize the total potential energy of the entire region of interest, we need to minimize the energy of the element also. So, what we do is that since we have already shown that this energy is a function of electric potential, here you can see 15.2. So what we are going saying is that let's take a triangular element. I'm again taking two-dimensional case. So let's take a triangular element, and we are assuming that the potentials at the three vertices phi 1, phi 2, phi 3. The coordinates are x1, y1, x2, y2, x3, y3. Here I have to tell you one thing, that every method follows certain convention. So when we say 1, 2, 3, we follow a certain convention. That is how we number the nodes. Because otherwise the formation of the equation will become a problem, because we are not doing manually, everything is automatic by programming. So some convention is followed. The convention here is that this numbering is always anti-clockwise. Like our target node, if it is 1, then 2 and 3 will be in anti-clockwise direction. You can clearly see here. This is a convention we will follow throughout. And if it is followed for the entire region of interest, then we can show that there will be no problem in deriving the equations. So with this we move forward. I have already said that our basic assumption is that it's not that the potential is varying between the two nodes. No, we are saying potential is varying linearly over the entire element. So phi of any point must be related to all the three nodal potentials, of course. So what we are writing here is, here you can see that equation 15.4, we are saying that phi is a linear equation which is varying with x and y over the entire element domain. Now, once we have defined this linear relationship, by the way, this could be a quadratic relationship. There is no harm in it. In fact, FEM has a quite clear derivation for quadratic one. So I am taking the linear one for your course, but as I said, more than 70% of the problems can be very efficiently solved with the help of this equation 15.4. Now, if I define phi in the elemental domain in this way, then within the element, I can define the x component of field intensity, which is the first order derivative, minus del b del x. And it should be del phi del x, I'm sorry, it's a typing mistake. So it is minus alpha 2. Similarly, the y component of field intensity is minus del phi del y is minus alpha 3. So now I go to the three vertices of the triangle, that is the three nodes. How do I write the equation of the node potential? Very simple. I follow equation 15.4. Then if I take node 1, its coordinate is x1, y1. So I write phi 1 is equal to alpha 1 plus alpha 2 x1 plus alpha 3 y1. If I take node 2, its coordinate is x2, y2. So phi 2 is alpha 1 plus alpha 2 x2 plus alpha 3 y2. And in the same way, phi 3. So these three node potentials together form equation 15.6, and these three node potentials are very important for us because we are going to develop the equation based on these three. Because as I said that our solutions will come only at the nodes. Rest of the points we will do the linear interpolation. So our target is now how do I get the coefficient alpha 2. Why I am interested in alpha 2? Because of equation 15.5. Why? Because we see that x component of field intensity is equal to minus alpha 2 and Ey is minus alpha 3. Now alpha 2 from 15.6 can be very easily obtained using Cramer's rule. Now Cramer's rule you can do better than me, so I have written it. And then I have expanded this determinants, that is equation 15.7, and the denominator I have written it as capital D, and if you expand the denominator this will equation 15.8, and if you recall your knowledge of coordinate geometry, then you will see that equation 15.8 is nothing but 2 times the area of the triangle. Similarly, from equation 15.6, I follow the same Cramer's rule, find out alpha 3, which is given in equation 15.9. Then I have to minimize the energy. For that, I need the value of E. If I know the two components of E, that is x and y, then E will be square root of ex square plus ey square. So here we are doing that E total is square root of ex square plus ey square. Now ex square is alpha 2 square, ey square is alpha 3 square. Then we say that the any element, if I mark it as T, then energy of that element is half of epsilon, which is epsilon 0 into epsilon r, then E square into the volume. In this case, A is the area of the triangle. So we get, now I substitute E square as alpha 2 square plus alpha 3 square. So now this becomes our functional. As I said that we have to minimize the functional. So equation 15.11 becomes our functional. Now when we have to minimize, then that We need a particular variable with respect to which we have to minimize. In our case, the target node is node 1, that is the vertex 1 of the triangle, and the potential is phi 1. So what we are doing is we are taking the derivative of the energy of the triangle with respect to phi 1 and equating it to 0. So then you can see that when we are taking the derivative, this volume does not have any relationship with phi 1, but alpha 2 and alpha 3, they have here, you can see 15.7 and 15.9, they have a term involving phi 1. So we write equation 15.12. And then this del alpha to del phi 1, then that we obtain from 15.9, sorry, 15.7, and del alpha 3 del phi 1 we obtain from 15.9, and that is written here. And in equation 15.11 and 15.12, this A is the area of the triangle, which is of course d by 2, because capital D is 2 times the area of the triangle. So we get del alpha 2 del phi 1 from equation 15.7. We get del alpha 3 del phi 1 from equation 15.9. 15.7 here and 15.9 here on your screen. Then what we do, we put everything together in equation 15.12 that you can see here. I am substituting del alpha to del phi 1 and del alpha 3 del phi 1 at the bottom of your screen in equation 15.12. So I get equation 15.13, and you can see that d cancels because d is definitely not 0. If d is 0, we cannot compute. So it is a finite element. That's why it is called a finite. It has a finite area also. So d cancels. Then we get this equation. So now what we are having this equation, we have alpha 2 into y2 minus y3 at the top of your screen. Look at my mouse moving, then alpha 3 into x3 minus x2. But we know the expression of alpha 2 and alpha 3 in terms of phi and coordinates. That is equation 15.7 and 15.9. We straight away bring in those equations here and substitute in equation 15.1. And we get this equation. Just simply substitution, you can clearly see here. Now, since right hand side is 0, so what we are doing is epsilon 0 being a pure universal constant, we are eliminating it. L is the length in the perpendicular direction, which is also not 0, so we are eliminating it. 2 is a constant, we are eliminating it. But we are not eliminating epsilon r, although for one particular element, epsilon r is equal to constant, but since this is material property, we are not eliminating it. Then d, this is straight away related to the element because it's 2 times the area of the triangle, so we are not eliminating it, we are keeping it in the equation. So we expand this equation 15.414a. How? That we write what is the coefficient of phi 1, what is the coefficient of phi 2, and what is the coefficient of phi 3. And if you look at equation 15.14b on your screen, you can see that the coefficient of phi 1, it is simply the coordinates of the vertices. So once the coordinates are known, I can get an expression, clear expression or a value for this coefficient. Similarly for phi 2 and similarly for phi 3. And just as a tip, I can say that if you look at these equations, you will always see that there is a cyclic order formation. Very clear, it is easy to follow that. So then what we say that finally, if you remember, look at this equation 15.4b. It is a linear equation. It involves only electric potential. That means it is a scalar variable. So it is same as that of the finite difference method, where we develop linear equations with scalar variables. So you can see that finally we have brought down the governing equation. In our case, it was the minimum energy condition to an equation which is a linear equation involving scalar quantities. So it's the same as that in the FDM. That is our target, that was to bring it down in this form, and we have achieved it. So we are writing a coefficient K1 for phi 1. T stands for the triangle, for a given triangle. Then K2 is another coefficient which is also for a given triangle. K3 is another coefficient for phi 3 which is for another triangle. So clearly we have three coefficients which are related to three the vertices or the three nodes phi 1, phi 2, phi 3. And then we write equation 15.16 where we write clearly the three coefficients and their expressions. And we can clearly see that these expressions have nothing but the coordinates, because area of the triangle is expressed in terms of the coordinates of the vertices. The other terms are also coordinates, and only one additional term is there, that is epsilon r, and that is a material property. So you can clearly see that how beautifully this equation has been developed. But now, how we use this equation, that is also very important to know. But for that, we have to again now see the nodal connectivity. I was telling you, now in FEM, different connectivities are used. Very commonly used are two types of connectivity. So you can see on your screen, on your left hand side, you can see it is a 6-element connectivity. It is called hexagonal connectivity, which is quite obvious. And on the right hand side, you can see it is a octagonal connectivity. Now, there is something in this connectivity I have to explain that in FDM, you remember we always said that node 0 is the target node. In the same way, in FEM also, when we assume the entire system, this node 0 is our target node based on which the derivation is done. So for the hexagonal connectivity, this node 0 is our target node. Then we see that in how many triangles this node 0 belongs. Quite clearly, node 0 belongs in 6 triangles. That's why it is hexagonal. On the right hand side, it's the octagonal connectivity. So node 0 belongs to how many triangles? The answer is 8. Then we have to mark these triangles. For example, in hexagonal, we mark it as T1, T2, T3, etc. That means triangle 1, triangle 2, etc. And in octagonal, T1, T2, etc. up to T8. Having said that, then we have to mark the node numbers in that anti-clockwise convention. So this target node 0 is always in equation 15.15, and at the bottom target node 0, it is always the phi 1, that is node 1. Then the other two nodes are 2 and 3, and they should be in anti-clockwise direction. So if you look at T1 of the figure, node 0 is node 1, then node 1 is node 2, node 2 is node 3. And if you take T2, then node 0 is node 1, node 2 is node 3, 2, and node 3 is node 3. If you take triangle 6, node 0 is node 1, node 6 is node 2, node 1 is node 3, the anticlockwise convention. So, and of course, in every triangle, we have to, as you can take the material property. In our case, it is the relative permittivity. That should be known, otherwise you cannot compute the field. Now, here an interesting observation can be done. If I ask you, or if you note carefully, you can see that the target node 0, that belongs to all the 6 triangles of the hexagonal connectivity. But all the other nodes, they belong to only 2 triangles. Look at the node 1. It belongs to triangle T1 and triangle T6. Or you look at node 2. It belongs to triangle T1 and triangle T2. Like that. Not only that, there is one more interesting point here. What is that? If you look carefully, triangle T1, then you will see that node 1 is, as per our definition, node 2. If you look T6, triangle 6, then node 1 is, as per our definition, node 3. If you look at, say, node 4, and if you look at triangle 3, then it is, as per our definition, node 3. If you take triangle 4, then as per our definition, this node 4 is our node 2. Or, in other words, what I am trying to tell you is that all the other nodes, they appear in 2 triangles, but in one triangle it appears as node 2 of our derivation. In another triangle it appears as node 3 of our derivation. That's the interesting point. Whereas the target node 0 appears in all the connected triangles, that is hexagonal means 6, octagonal means 8. Based on this observation, the next equation is formed. This is explained in this paragraph. That so now, how do I write the equation? I take triangle T1 and I apply equation 15.15. How? Because triangle T1, the 3 coordinates are known. So I can write K1T as per this equation, as per the coordinates. Then equation K1T into phi 1. Now it will be K11 because triangle is 1. Then phi 2 in this case will be phi 1. So K11 into phi 0, that's the first term. Then K21, because T transfer triangle 1, so K21 into phi 1. And K21 can be obtained from equation 15.16. Then K31, which is for triangle 1, into phi 2, because phi 2 is the node 3 in triangle 1. And K31 can be obtained from equation 15.16. So I repeat, what will be the equation? It will be K11 into phi 0, K21 into phi 1, K31 into phi 2. This is for triangle 1. But if I go to triangle 2, then what happens? I write K12, 2 stands for the triangle, K12 into phi 0, K22 into phi 2, because now phi 2 is node 2, K32 into phi 3, because phi 3 is node 3. So in this way, I can write all the equations, and if I look carefully in this, I will see that this phi 0 will always be multiplied by K11, K12, K13 up to K16. So if I write all the 6 triangular equations, this phi 0 will have 6 coefficients, but all others, node potentials, will have 2 coefficients because all other nodes belong to 2 triangles only. So when I have written the equation in details, you see phi 0, the last term here, this will have 6 terms, so it is written as F0 at the bottom, summation of K1t, and t varies from 1 to 6. That means it will be K11 plus K12 plus K13 up to K16 because phi 0 belongs to all the 6 triangles. But phi 1 belongs to phi 1 here belongs to T1 and T6. In T1 it is node 2, so the coefficient will be K21, but it belongs to T6 as the node 3, so it will be K36. So you can see here phi 1, it is K2 triangle 1, K3 triangle 6. Similarly phi 2 will be, it belongs to triangle 1 as node 3 and triangle 2 as node 2. So you can say F2 is the coefficient of phi 2. So F2 is K2 into T2 and K3 of T1. In this way, all the 6 node potentials, phi 1, phi 2 up to 6, that means here phi 1, phi 2, phi 3, phi 4, phi 6, they will have coefficients F1, F2, F3 up to F6, and they will be summation of 2 coefficients. And these 2 coefficients are as per equation 15.15 here on your screen. Therefore, finally, I have that based on the connectivity, I have the equation 15.17, which is also a linear equation, and it involves scalar quantity, that is electric potential. So now, if I go to that original diagram, so you can see here, this every node, if I which have unknown potential, if that is the target node, there will be 6 nodes connected to it. So I write that equation, whatever I have explained. Then I go to the next node, it will also have such 6 nodal connectivity. I will write that equation. So in this way, for all the nodes, I will write what? I will write this expression. Equation 15.17 for all the nodes. Taking the node where I am writing the equation as the target node, so that will represent phi 0, and all the other 6 nodes or 8 nodes, depending on the connectivity, as phi 1, phi 2, etc., and we will get the coefficients from the coordinates and the material property. And therefore, if I have 100 target nodes whose potential is unknown, I can write 100 equations. And so if I have 100 equation and 100 unknowns, I can solve this. This is very basic knowledge. And therefore the problem is solved. I can get the value of the unknown node potentials. Once I get it, then within a triangle, that means within any triangle, if I know already now, if I know phi 0, phi 1, phi 2 after the solution, then within a triangle T1, what I have to do? I have to use equation 15.4 and I can get the potential at any point. And I can calculate alpha 2 and alpha 3. How? Alpha 2 is 15.7 and 15.9, and then these two will become the 2 components of the field intensity. So you can see that how easily I can get the other quantities while once these nodal potentials are solved. How? First, we use equation 15.15 to develop equation 15.17 for one nodal connectivity of 6 or 8 elements, and then we extend it to all the target nodes for which potential is unknown. We write, let's say, n number of equations for n number of unknown node potentials, solve it, get the node potentials, then apply that linear interpolation equation as already shown on your screen, 15.4, and then you can get the values of electric field intensity also as the first order derivative. So our problem is solved. This is the beauty of the uh, FEM formulation using variational approach. I will not discuss Galerkin's approach in this class because that is too, I mean, too much lengthy. I would not say lengthy, too much involved in this course. It's not needed. So next comes the multi-dielectric, but that I will do in my next class. So I hope I could explain, but before I uh, do that, let me just share one more file to you. Where is that? Yeah, just a minute. Yes. So let me share it. This is that to show you that how we subdivide in FEM. Now hopefully it will come on your screen. I hope it is coming on your screen.
Yes, sir.
So you can see here that how we are subdividing. These are all practical examples. These are not theoretical one. This is a typical circuit breaker contact. Can you identify the circuit breaker contact? See this white one here. You can see my mouse moving here. By the way, this is only half of it. So this white one is actually the moving contact. In circuit breaker, I think you are now studying switchgear. There will be two contacts. One is called the fixed contact, the other is called the moving contact. The moving contact moves and thereby closes and opens it. So this is the moving contact and this is the fixed contact. So you can see the gap because on the left hand side there is other half. The moving contact moves through this gap and then it fixes, and then we have the connectivity or the connection that is switched on. But now here this is the connectivity, and by the way this is not generated by me, this is generated by software. Now in this diagram what I am trying to show you is very interesting. You can see that the softwares today are so smart that they know where you use the finer elements, where we use the larger elements. So you can see here where my mouse is moving that here the gap between the two electrode is less, so field will be high or field will be non-linear. So they have used very finer meshes. And otherwise, near the boundaries, they have also used finer meshes. But you can see as we are moving away from the electrodes, it has used very large meshes. This is the typical compromise so that we don't get very large number of mesh or the elements. This is one I have the diagram. Then this is once again another aspect. This our today mesh generators, they are another way very smart. That is, once you say that generate the mesh after defining the geometry, they will produce a what is called a draft mesh. It's like a letter that first we produce a draft and then we fine tune it and make the final one. So this is the draft mesh. Now, if you are not happy with that, you can tell the software that certain things to be changed, and then the software will generate a finer mesh. So here it is the finer mesh where you can see that the areas where the field is expected to be high, they have generated very, very fine mesh. Particularly in this is that area which is very critical. So you can see where the mouse is moving. This is very fine mesh, so that our basic assumption that within one element potential varies linearly will hold true. And this one, uh, uh, let me see how it is happening. Yeah, see, now you can see here a little bit enlarged. See here, it's very fine mesh. So we are expecting good results over here. So this mesh generators, in this way, we can of course, uh, refine it. This is another diagram I'm showing. This is, you can see the two electrodes where you have at the top one electrode, my mouse is moving. On the bottom you have another electrode, and in between you have an insulator, the vertical one. This is called a support type insulator, that vertical support type, and a mesh is being generated. And uh, this is what we do for the mesh generation. And this is another diagram. Correct here. See here, it's the porcelain bushing, very detailed diagram. Well, you can see here, let me show you that I have shown you yesterday, I mean in our last class, that actual broken bushing, where I said that at the center you have the conductor. So horizontally here the conductor is shown at the axis. You can see here, this is the conductor which is going from outside into the tank. It's a transformer bushing, or typical porcelain bushing that I have showed you earlier. And then here there is a paper insulation. This is the white one, is the conductor. Before that you can see, let me see how I can increase it. Uh, if you can see here, the white one is the conductor. Then there is one horizontal, you can see, this is the paper insulation, which I showed the photograph in the last class. And then this is the porcelain housing. And I told you that there is a gap between porcelain housing and the paper where we have oil. And this is that small gap you can see here. And this is the tank, the rectangular type. Inside we have oil. And outside the porcelain we have air. So we have subdivided the entire thing here, and this is how here we solve this problem. So this gives you some idea about this. I want to show you one more thing to you. Let me see where I have it. Let me see. Yeah, let me share it. In our previous discussion, I told you that how we bring in the fictitious boundaries. This is exactly the explanation of that fictitious boundaries. How? Typically, say this is the electrode, is whether it is a cylinder or a sphere, then we have earth, and this is an open-ended, unbounded field extended up to infinity. But we cannot solve up to infinity. So we have a knowledge that as we move away from the conductors, the field varies much less sharply. And if we are adequately far enough, that means the distance x is much higher compared to the radius of these electrodes, then the field becomes field variation becomes very slow. So if I plot with respect to x, the variation of potential will almost becomes parallel to x-axis. Now what does that mean? It means that if I have this a boundary vertical line, and if I take 2 points, 7 and 8 on both sides of these boundaries. But since potential variation is almost parallel to x-axis, what I can say is the potential V7 will be equal to V8. So we are bringing in a fictitious boundary condition. There is no boundary here. We are bringing in the boundary and we are telling that, let's say that is a boundary, then on both the sides I have two nodes having same potential. And that's how we end our region of interest without going up to infinity, with by bringing in this fictitious boundary condition. But from our knowledge of field, we know that this is quite a practical approach, so we don't get any sort of big error because of this bringing in fictitious boundaries. So what we actually are doing here, you can clearly see that whatever I was showing you today, then again if I go back to that, then you will see, let me just show you. Yeah. So once again I'm showing you the today's diagram. Yeah, here. Now it will be coming on your screen again. Now you can see this circuit breaker contacts. You can see that these are the two circuit breaker contacts. We are mostly concerned about this, not concerned about what is happening far away. So we have brought in fictitious boundaries. As you can see, my mouse is moving. These are fictitious boundaries, and with the assumption that if you take two nodes just on the other side of this boundary, the potential will be remaining same. In this way, we actually solve all such problems. For example, this one, here you can see. This circular boundary is in this case our fictitious boundary, where again we are assuming that same boundary, fictitious boundary condition of equal potential or very small potential variation. Same way here you can see that from the porcelain, how far I will go. Otherwise, the number of nodes will be infinity. So here we have brought again fictitious boundary. Here you can see my mouse moving, and we have assumed that fictitious boundary condition. This is something we have to bring in our field computation. Otherwise, you cannot compute. By the way, nowadays you don't have to write all that. Software packages, particularly the FEM packages, which are so powerful, these are built in. So that what you do is you choose appropriate boundary condition and the software takes care of that. So I think here I will stop today. Any questions from your side? Okay, so I'm stopping today. There will be no class this week because I'm very busy this week. So in the end of this week, I will again write to you with the options for the dates of the next classes. Thank you. You can log off now.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.